Today, I think the topic of my talk is neural representation learning in natural language processing. So I think I will take about 60 minutes to introduce some important concepts that you must know if you want to implement some sort of models to learn the sentence representation or to learn the word representation. You should know this may be important concept. Okay, so at the first steps, so here when it comes to the neural representation learning for natural language processing, what does it mean? It just means given a text, the text could be the word, a sentence, or a document. We want to use a deep neural network to convert this text into a vector. Most of the time, it could be a low dimensional vector. So based on the different granularities of the input text, we have the different maybe scenarios for the representation learning. For example, the word representation, the phrase level, sentence level, or even the sentence pair level. So in this talk, I would like to focus on the representation learning for the word and the sentence. The reason is because these two are quite fundamental steps which could pave the way for the representation learning of the phrase or even the document or the sentence pair. Yeah, you just keep this in mind. These two granularities are fundamental steps. Okay, let's move on to the first part, the word representation learning. So start with this question: what is the word representation learning? It's very easy, very intuitive answer. That it is a vector. We just want to convert this discrete signal into a vector. So for example, here we have an apple and we convert the apple into a three-dimensional vector. The next question is, why should we learn the word representation? So although maybe there are a bunch of reasons why we should use the word representation, but here I just pick up some of the points. One is it would be easy for us to maybe to make the mathematical calculation. For example, supposing you have already know the word representation for these two words, for the red and apple, how could you calculate the representation of this phrase? So here is a solution. So we can regard the representation of the phrase as the output of the function which take red and apple as input. I mean, you can design the semantic compositional function, and this semantic compositional function could help you to obtain the phrase level representation. So you can also apply this rule. I mean, when you have already get the phrase level representation, you could use them to get the sentence level representation. It's a very cool thing, right? Because, you know, giving you any sentence, you could convert this sentence into a vector. This vector is something like a feature vector, which just characterize the informative information of this sentence. So you can use this vector to do anything. You can use it to conduct the sentiment classification task. You also could use this vector to retrieve some maybe semantically closed sentence. That is a task. We call it as a semantic matching. So the general idea is if you could vectorize some discrete signals, and which could make many things more easier. So far we have know what and why. The next question is how. How can we get the word representation? So I could maybe at least list more than 100 methods which can use to learn the word representation. For example, here I just list a couple of them. Yeah, indeed, a lot of approaches to learn the word representation. So how can we understand this different method? No worry about it. Let's try to cluster them. I mean, so we could use some principles and we could cluster these different methods. The first principle is, are these are these approaches symbolic or distributed? The symbolic representation usually is a one-hot vector. And there are two characteristics of this one-hot vector. The first is the vector size usually equals the size of a predefined vocabulary. The second characteristic is all of these vectors are filled with 0 except one take the value of 1. So, and most of the time, the index of the value 1 is exactly the index of the word in this vocabulary. So, you know, for the symbolic word representation, each dimension of this vector is explainable. However, for the distributed representation, you cannot explain the specific or one element in this vector, but the whole vector could be explained. It's just represent a point in a latent space. Okay, that is maybe a general idea of the symbolic and distributed method. If we apply this rule to cluster of these approaches, you will find that, okay, we have two clusters. Only one hot is symbolic, which means most of our existing methods, they are something like the distributed word representation. Okay, the next rule, the next principle is, are these approaches supervised or unsupervised? It's very easy and intuitive category, right? So the supervised method means maybe you should learn the word representation based on some labeled data, while the unsupervised method indicates that, okay, you don't need some labeled data, just you can train your word representation on a bunch of unlabeled data. Yeah, here also there is another case. That is, we call it as the semi-supervised learning. It means sometimes we could first use the unsupervised pre-trained embeddings, and then we can fine-tune these pre-trained embeddings based on a specific task. The task could be motion translation, sentiment classification, and all of the tasks you could use. So let's try to cluster the approaches by this principle. Yeah, and we get 3 clusters. The red circles highlight maybe the unsupervised method, and the blue circle highlight the semi-supervised method. Here there are only one supervised method, empty embedding, which means we first training a motion translation model, and the embedding matrix would be taken out as a byproduct. And most of the time we don't use the completely supervised pre-trained embedding. However, sometimes it would be useful in terms of the semi-supervised embedding. For example, you can see there are 2 models. Senti-EMB means the sentiment classification based word representation learning. You first use unsupervised pre-trained model, and you fine-tune this pre-trained embedding based on a sentiment classification task. However, the curves, this word representation means you fine-tune your word representation based on a motion translation task. So yeah, in general, you can find a lot of existing methods are relating to the unsupervised method. So let's dive into this part. Continue to using another rule, that is, are these approaches contextualized or non-contextualized? So it's a very popular concept currently. So the non-contextualized pre-trained embedding means the word vector is a context independent. So means the word vector will not change even its context word has changed. So that's the definition of the non-contextual word representation. So in terms of the contextualized word representation, which means each vector of the word is content dependent. So even you have the same word, if the word appeared in the different context, then the word representation would be changed. That's the maybe the general idea along this dimension. So if we apply this rule, and we can find that there are two clusters. Some of them, such as you maybe find some models which are familiar to you, such as the globe, water vector, and these models are non-contextualized approaches, while some models such as the BERT, ELMO, BERT, these three are belonging to the contextualized pre-trained models. Yeah, so we could continue to, the divide or partition this method, and the rule is count-based and prediction-based. It will be very interesting settings. The count-based models, the general workflow of the count-based model is firstly you should construct a word content concurrence matrix, and you use some matrix decomposition methods such as SVD to get the low dimensional representation of each word. So that is something about the count-based method. So for the prediction-based method, we frequently refer to a neural network and learn a word representation in the context of the language modeling task. You can see here, we just clustered the existing non-contextualized models based on the count-based or prediction-based. You will find you have two different models, and most of some models, some familiar models such as word-to-vector, globe, it could be classified into the prediction-based models. And you also could find there is overlapping between these two clusters. Yeah, the globe, this model could be regarded as an intermediate state between these two approaches. So why would this happen? Because some researchers, they just find that okay, there is a strong connection between the count-based method and the prediction-based method, which would be very, very interesting findings. It just means okay, you can unify these two different approaches in some maybe perspective, and you can refer to more detail if you are interested in this by these papers. So okay, so in what follows, I just want to maybe these models, I highlighted by the circle. These models are very maybe popular here. It would be worthwhile. It was worthwhile for us to know some details about these models. So here, as you can see, I make a collection of the maybe the word of the papers relating to the word representation learning. There are totally maybe more than 200 papers, and if you rank these papers by this citation, and you will find a very interesting thing is, so maybe the first the most cited papers is the word vector. Or the top two papers are proposing the word to vector models. The third one is the globe. The first one is neural language models, then followed by the BERT and the ELMO. So yeah, it's really worthwhile for us to know some details of this model. The first is the neural probabilistic language model. If you are, I think if you are interested in the neural models for the natural language processing, you must know these papers. It's one of the earliest work on neural word representation. So as early as in the maybe almost 50 years ago. And actually, the main motivation or the main contribution of this work is they want to neuralize the language model task. I mean, they want to design a neural network framework to solve the language model task. And then the word embedding is just a byproduct. So that's why maybe for this model, it's not very efficient to train. It's very slow. If you want to, maybe cannot be extended to a large data set. But it's still very famous, right? Because it's just make a good starting point. So this work, maybe everyone would be more familiar to this work. We call it over the word vector. So this work actually consists of two specific models. One is the Symbolic, the continuous back of words, Symbolic, and another framework is a Skipgram. So for the general idea of the Symbolic is they just claim that given a target word, the target word should be accurately predicted by its context word. That's the general idea of the Symbolic. However, for the Skipgram, they just claim that given a target word WT, it could predict its context word, such as the W T-2, T-1. This is just a two learning perspective for the model. It's very intuitive. Another thing is, so previous work, the main goal is the language model task. However, for this paper, they just focus on learn the word repetition. So they could use a lot of tricks to accelerate the training process. So I mean, if you want to use this software, it's very efficient for you to train on a larger data set. Then another famous work in terms of the non-contextualized word repetition is the globe. So the globe, actually this work is a little late compared with the word vector, but this work made a good analysis. And one contribution is it just built the connection between the dot product of two words embedding with the co-occurrence. So here I just list his optimized objective function, something like the just measure the relationship between the dot product of two word representation and a function of its co-occurrence. So if you are interested in this model, this work just has set up an awesome project homepage. You could download maybe different setting word representation from its homepage. So previously we just highlight some detail some non-contextualized pre-trained models. Yeah, currently the contextualized word representation are really popular and are really useful. So we also shoot some of them. The first is the ELMO. So the ELMO, the basic idea of the ELMO, or the basic idea of the contextualized word representation could be summarized from this figure. As you can see, this figure just illustrates the workflow of the task language model. We have some input word I will go to, and the goal is you want to predict what the next word is. So your first thing you do is you have a lookup table. You convert each word into a vector based on the lookup table, right? And then you get the WI for each word. You have representation WI. It is a vector. Okay, then you continue to use a recurrent neural network to convert each WI into a HI. In this step, you could contextualize each word representation. You just model the interaction between the different words. So finally, you have a HI. Okay, so why I want to highlight this workflow, because we can explain what is a non-contextualized is and what is a contextualized is. So the general idea of the non-contextualized word representation is we could only use the lookup table, the theta word. That's the things we want to use. So if we have the lookup table, we could convert any words into a vector, right? But you know, these words are content independent. They have no interaction between each others. So then we just have a question, why not use the recurrent, also use the theta NNLM? We also could use the recurrent neural network layers. Why don't we use HI as a word representation instead of the WI? So that's maybe the major idea of the contextualized word representation. Instead of taking WI as a word representation, we use HI. So you also find if you use HI as a word representation, you will have some additional cost. That is, the first thing is you have more parameters, because if you want to obtain HI, you should have a recurrent neural network layer. You have a theta, so you will have more parameters. And definitely, second, the whole model will be, slowly to train, because the recurrent neural network is compared with the lookup table operation. Yeah, it's relatively slow. But the advantage is if you use the contextualized word representation, it could help you to disambiguate some words with multiple senses. So that's the general maybe descriptions between the contextualized and the non-contextualized. So you could just keep this in mind. If you use the contextualized word representation, you will have more parameters, because instead of the theta word, you also have the theta. So that's the basic idea of the MO. So maybe more precisely, if you instantiate the recurrent neural network with a multi-directional LSTM, and also training this model on large data set, then it could be a MO. And definitely you could stack multiple recurrent layers, right? Instead of only one, you could use multiple layers. That's just the basic idea of MO. So let's see what the BERT has said. So for the BERT, one different thing is instead of using the recurrent neural network, they use a transformer, because transformer will be more efficient to train. So that's the one maybe a modification of the BERT compared with the MO. Another thing is you can see they have two objective functions. One is masked word prediction. Another is next sentence predictions. So the masked word prediction means they just randomly mask some word, and they want to use their context information to predict what the word is. By contrast, the next sentence prediction means we want to, based on the representation of this sentence, to predict the next sentence. So that's maybe the two major objective function of the BERT. So another thing, another characteristic is you just keep this in mind. You use the transformer as an encoder instead of the by LSTM. The reason is because it's very efficient to train. So also, in terms of the data set, they have used a lot of unsupervised data set. So far we have detailed some existing famous model, word vector, globe, NNLM, ELMO, and BERT. If you, and this question could be, how can I use them? Here I share some links, and it's not very difficult for you to track the resources of this software or models or training corpus. You could find them by searching the Google. But here I just highlighted some of the links. Maybe another important question is, since we have maybe a bunch of pre-trained method, how can we make different choices based on different scenarios? So I share some of my experience. The first thing is, under this, maybe under these conditions, you don't need to use the pre-trained models. For example, if you focus on the language model, maybe you don't need to use the BERT or use the word vector. Another task is the motion translation. Most of the time, you don't need to do the pre-trained models. Maybe in some scenarios, even the motion translation task also benefit from the pre-trained word embedding. So another is maybe under these conditions, it would be useful if you use the non-contextualized word representation. The non-contextualized word representation means the word vector. You could use the word vector. You also could use the globes. So the first case is, if you are limited, you have a limited computational resources. You don't have you don't have a lot of GPU cards. You just use the word vector or globe. Secondly, if you want to achieve faster training, or if you want to quickly evaluate your models, use the word vector would be better. So another thing, definitely, if you don't have the off-the-shelf BERT models, just use the word vector or globe. Another thing is, even you have already downloaded the BERT models or the BERT parameters, but the task you are interested in, if your task you are interested in has some huge domain shift with the domain that the existing BERT model trained, if they have some huge domain shift, it would be the solution is you should train a pre-trained model based on the domain you are interested in. For example, if you want to do some, if you want to do some text classification task on the Twitter domain, but you only have a BERT in the NewsWire domain, so maybe under this scenario, maybe BERT would be would not be the best choices. The better thing would be you just train a word vector or you train a globe on the Twitter domain and then use it. And definitely, if you could train a BERT or ELMO model on the Twitter domain, definitely it could be better. But pre-training the contextual model usually, they require expensive, computational resources. So it depends on your choice, depends on your own resources. Lastly, is best of both worlds. Even you use the BERT, you also could use the globe. You also could use the word vector. And in many NLP tasks, one observation is there is some complementary between these two types of word representation. For example, if you are interested in the tagging task, some lexical level task, the tagging, the NER task or the trunking, you just combine word vector or globe with the BERT, and then you would be you would be maybe get some better performance. So then in terms of the contextual word repetition, when you should use them, the first is, yeah, definitely if you are rich in the GPUs, if you really care about the sort of results, you don't care the training time, you just use the BERT. Most of the time you will get a awesome result. Yeah, another requirement is you should have off-the-shelf BERT pre-trained parameters. The last point is also very crucial. So the contextual models such as the BERT always could improve the generalization ability of your models. So if you don't have many training samples, you just have a couple of them, using the BERT always would be a better choice. It could improve the generalizability of your models. Okay, that's maybe all the things I want to share in the first part. So then let's dive into the representation learning of the sentence. So also, we just start with the questions. The first is what? What is a sentence repetition? It's very easy to understand, yeah, give a sentence. You want to design the different composition function, then convert this sentence into a vector. So why do we need the sentence representation? Also very easy. It's a really fundamental step. Most of natural language processing tasks.
Pengfei, okay. How about we take questions on word representations before?
Okay, yeah, cool. I mean, so far, do you have some questions in terms of word representation?
Yeah, I have one question. So we were discussing yesterday with Antonis about how distributed representations don't just capture, they capture the part of speech of the word. They'll also capture the synonyms. They'll also capture a lot of information. I'm just wondering, where does it learn all of these information from? Does it just learn it from an untagged corpus? Like it learns everything, like part of speech and synonyms and everything.
So it means something like why could they learn this type of information, right? So actually, it depends on the different types of your context. I mean, if you have the different types of the context, you will also have learned the different types of information. For example, in terms of the word to vector, we usually have predefined a window size, right? So the window size is something like a context information. So if you extend the window size to maybe the whole document or the whole sentence, then the representation you have learned just express something like the topical information or topic information. I mean, maybe if you can also change the window size to maybe 2, 3 more, some smaller one, and then in this maybe scenario, the representation you learned just express some maybe lexical information such as the part of speech or something others. Yeah, so they indeed could learn some different types of information, and this phenomenon can be more clearly observed in the contextual word repetition. So I mean, a lot of existing papers, they just investigate what types of information that BERT has learned, maybe different layers just express the different information. Some low layers just contain some syntactic information, maybe or lexical information, maybe the top layers express some semantic information. Yeah, I just the first thing is they indeed has learned the different types of information, but how or why can they learn? Oh, maybe I mean the predict contact predict or predict what the next word is a really intriguing task. It's a powerful task. It's really difficult. If you can do this, you should master a lot of background knowledge. And you know, we just use this task to instruct our model to learn the background knowledge. I mean, maybe, yeah.
I was going to add, if you remember from this morning's presentation where Lori discussed, for example, how linguists decided, like come up with tests to figure out what is a determiner and what is an adjective and what is a noun, right? And then we said, for example, that determiners, or like, what was it? Like nouns get determiners, or they are modified by adjectives, or nouns tend to be like the subject or the objects of verbs. And you can think of this, even these are like very concrete things. These are actually things that happen in text everywhere, right? So no matter what text you get in any language, it will have this type of structure. So if you just get random text, and not random text, like, you know, properly formatted text, like that humans have created, and then you try to predict words that are missing or the next word, or, you know, something like that, then if you think about it, in order to be able to do that, then in a sense, you need to be able to capture that information, right? So that's why these very simple tasks, like predicting the next word or predicting a missing word, or, you know, given the context, predict the word, or given the word, predict the context, can be very, very powerful for capturing these types of relations between words. But also then they can also be even more powerful. So they won't just capture something like, you know, their part of speech tags. But if you think about it, as Pengfei said, because context matters a lot, right? Like a book and a library will very often be in the same context, right? A book and a car, they might be in the same context. Like I left my book in the car or something, but a book and, well, I guess a book is a bad word because you could have a book about everything. So you could collocate with any book,
Yeah.
any word. But let's say, I don't know, give me an example, like, let's see, if you're an Italian, a cappuccino and the evening shouldn't go together, right? They shouldn't appear in the same context. Cappuccino is something for the morning. So anyway, just an example, like there's, you know, if we're talking about monarchy and about kings and queens, then these kind of like appear together, right? In these very similar contexts. So we can also learn relations between words and about the domain that they are in, and so forth, just by looking at their co-occurrences in text. And these tasks, like these like simple tasks like predicting the next word and stuff, essentially require you that you're able to do that, right?
Yeah.
So.
Yeah, I think Antonis gave a really, a clear explanation. So predict what the next word is a simple task, but if you want to do it better, it's really not simple. So yeah, but we want our model can do it better. So our model should know a lot of other information. It could be syntax, it could be semantic, it could be everything. It's just you just give your model a really hard task. It should master a lot of background. Okay. Any other questions?
Can you speak a little bit about how multilingual vector representations work?
Multilingual or the representative could work?
Yeah.
Maybe Antonis would be more better in this domain. Actually, I'm not really sure how to, to learn across lingual word representation, or how build the connection between the the different language in terms of the word representation?
Yeah, so they would be very different, right? So if you think
Yeah.
about this, it would very much depend on the language. In the same way that, you know, when we talked about part of speech, different languages have different part of speech, and different languages have very different morphology.
Mm-hmm.
So there are ways, like, you know, there's, you know, Peng Fei mentioned BERT. There's also multilingual BERT, which is essentially the exact same model, just trained on 104 or 106 languages, if I remember correctly, right? And by doing that, like, you know, by training over all of these different languages, I guess the intuition of why this could somewhat help is, you know, overall, like, language, just what it does, what does it do? It conveys information, right? And the underlying information is the same, like in terms of meaning, right? Regardless of language. And that's why, you know, translation works. So at the same time, there's many languages that exhibit similar phenomena in terms of, like, very simple things like word order. Like, you know, several languages are subject, verb, object. Others are subject, object, verb. But, you know, you can train on multiple languages, and hopefully the model will be able to figure things out and how they work across different languages. The other thing is that quite often languages share, if they're related, they would also share words, right? Like
Number or something like that.
yeah. So if you think of the text representation, like if you write the numbers with the Arabic numerals, like the standard, like 1, 2, 3 that we've been using, these will be the same across languages. Quite often, like named entities like Google or Amazon and stuff, you might not transliterate them, but you write them with the same, like, you know, with the Latin script that they were originally coined in. So learning, basically training a model with all of these data together and having some of the words, even just a little bit, be actually the same across languages helps you create, essentially, instead of learning like a single space that is different from language to language, it actually helps you to kind of like align the two spaces. If you think of like a space as, like, you know, the representation, which is just vectors, right? Now, there are a lot of techniques with which, even if you have monolingually trained representations, you can align them so that the representation for cat in English is the same for the representation for the Swahili word for cat or for the Greek word for cat. And these can also be very, very good. But again, they might not work as well if the languages are very, very different in terms of morphology. Okay,
Mm-hmm.
so that's also something to think about. If you're interested more in this, I think we can talk about it later. I think it's slightly more advanced than what we have planned, but it's something that definitely we should be thinking about. It's super interesting, like this whole idea that if you think about it, like you take a bunch of English text and you learn word representations, right? And the way that these word representations look like is that, you know, like dog and dogs and gods are like in one space, king and queen are in a different space, all the verbs are in a different space, and so forth. And then you have this English space. And then you go and you take Swahili, all right? And you now have the Swahili words, I'm sorry, I don't know them, for like dog and dogs and cats and lions, etc. And they're all there. And then you have the Swahili words for some of the verbs that you're using. And then you have the Swahili words for like king and queen. And, you know, if you just look at them, you're like, okay, these are two completely different spaces. But the interesting thing is that the spaces are somewhat what we call isomorphic. So the relation between dog and dogs or dog and cat in the Swahili space, because they're semantically very similar, the relation will be very similar to the relation that they have in the English space. And similarly, you know, the relation between king and queen would be more or less similar to the English one. And we can exploit these similarities in order to actually align these two spaces so that they actually map together.
Yeah, sound very interesting. I mean, this this setting.
Yeah, so we can talk about it more, Kathleen, if it's something that you're interested in. It's super cool.
Yeah, especially try to visualize them. Okay. Okay, maybe I think I could move on to next part. Okay, the next part is the sentence representation. So yeah, so maybe I just discuss why do we need the sentence representation? Yeah, because it's really a fundamental step. Most of existing NLP tasks could be formulated into a sentence representation problem, such as a sentence classification and a semantic matching and some other tasks. Yeah, the next question is also, how can we learn a sentence representation? Yeah, I also could list at least more than 100 methods to do these things. For example, here I highlight some of them. Maybe you are very familiar with these typical models: neural backwards convolution neural network, RNN, CNN, and LSTM, GRU, transformer or graph, GNN. So a lot of approaches, right? But just no worry. Again, let's try to cluster them. The first principle is very easy. Also, supervised. Are these approaches supervised or unsupervised? A supervised method means you don't need. You need level data, while the unsupervised method means you don't need any other level data. So let's try to apply this rule, and you have two clusters. So here, there is a very interesting phenomenon, that is, if you record clearly, so in terms of the word representation, many methods are unsupervised. However, in terms of the sentence level representation, most of the methods are supervised. Here, I highlight two unsupervised methods. One is a paragraph filter and a skip sort. And you just keep this in mind. If you want to obtain the representation of a sentence with some unsupervised method, you could try to use these two software. So here, let's focus more on the supervised method. So the next principle we could cluster these approaches is what types of structural bias this approach has adopted. So what is a structural bias? It is a set of prior knowledge incorporated into your model design. When you want to design a model to learn a sentence representation, you really should incorporate some assumptions or bias. So we could understand the structural bias from two perspectives. The first is the connection way, another is the topological structure. So what is a connection way? So in terms of the connection ways, you have two choices. You could design two types of bias. The one is a local, which means the local bias says here it is a sequence of words. W1, W2 is a sequence of words, and the local bias says each word could only interact with its nearest neighbors, while the non-local bias said each word could interact with some distant neighbors. That is the two choices you could use when you want to design a sentence level method to learn the representation. So another is the topological structure. The topological structure asks the question that along what structure are the sentence modeled. So you have these three choices. When you want to learn the sentence representation, you could assume the different structure of the sentence. You could claim that, okay, the sentence could be modeled sequentially, or you could also claim that, okay, this sentence should be learned along a tree structure or a graph structure. Then so far we have highlighted this different two aspects in terms of the structure bias. So we have the two choices of the connection way, three choices of the topological structure. So what if we combine the local and the sequential? We choose the local as the connection way and choose the sequential as the topological structure. Then we have these two models. The first part is recurrent neural network and some maybe its variants such as the LSTM and the GRU and some other ARM-based models. Another is the convolution neural networks. So, for these two types of models, each word can only interact with its neighbors, maybe the previous word, or the words within a window size. So, and then also both models just follow a sequential structure. They assume that the sentence should exhibit a sequential structure. So that's the first case. So what if we choose the non-local and the tree? So then we have these three models. Some models such as the recursive neural network, tree structure LSTM, or tree structure RNN, or the tree structure CNN. So for this model, they just claim that any two words could connect with each other if they have an edge in a tree, in a predefined tree. And most of the time, the tree structure is instantiated as a syntactic tree, such as, you can predefine the tree structure based on the dependency structure of the sentence or constituency structure of the sentence. You could use a parser to parse the sentence and you can get the tree. So what if we combine the non-local and the graph? So that is the main idea of the graph neural networks. So you could, for the graph neural network, any two words could interact with each other only if there is an edge in your predefined graph. So the main question could be, how can we define the graph? Most of the time, you could refer to some external tools. You could use a coreference graph or use some others. You also could use a syntactic tree to instantiate your graph. So that's the basic idea of the graph neural network. So another thing is, another combination is, what if we both have the local and non-local bias, and we also assume that the sequence, we also assume that the sentence follow a sequential structure. So one example could be attention LSTM. So it is a LSTM augmented with the attention mechanism. So attention mechanism could allow different words could interact with others. So here is a trick, that is, if your model has used the attention mechanism, which just means you have incorporated the non-local bias into your model. Here is a very interesting thing. What if you don't assume the local and non-local bias, and you also have no assumption in terms of topological structure? Here is a very, very efficient, simple, but a decent baseline, that is UNBO, or we call it as a neuron bank of words. It's as simple as just averaging the word repetition of all the words. And most of the time, this baseline could work pretty well, and it's very easy to implement. And especially on some tasks such as text classification, it could work pretty well. So if you want to implement some ideas, maybe you could try to do this model first, and then it can help you verify the effectiveness of your code framework. Okay, previously I just high level to introduce the different models. Here I want to detail some important points of the RN or of the CN by give some case study. So in terms of the recurrent neural network, there's something you should know. That is, you could use a recurrent neural network to get the word level and the sentence level representation. So what does it mean? So in many NLP tasks, some of NLP tasks could be regarded as a word level prediction, and some other NLP tasks could be regarded as the sentence level prediction, which means, okay, you can use a recurrent neural network to solve these two types of a task, because you can both aggregate the word level information and the sentence level information. That's the first point. The second is vanilla recurrent network are really not good at handle the long sentence. So that's why more than 100 papers, they try to improve some recurrent variance. You have two the typical example, the LSTM, the GRU. And the basic idea of this type of model is they just introduce some getting mechanism. So that's the whole, maybe the whole picture in terms of the recurrent network. If you want to get any more details, you could refer to the specific papers. So another thing is there's something you should know about the convolutional neural networks. The first is there are two types of convolution, 1D and 2D. It depends on the different types of your input signal. If 1D just means okay, the dimension of your input signal is a vector. So what if you want to process maybe a matrix? So you just use a 2D convolution node. So you should know they have two scenarios, and it depends on the thing you want to solve. Another concept in terms of CNN is, okay, they have the narrow, equal, and the wide convolution operations. So it is based on what types of padding mechanism you have used. So maybe if the length of your output vector is less than the length of the input vector, then we call it as a narrow. The same rule applies to the other cases. Such, if the input vector and the output vector has the same length, we call it the equal, and then otherwise we call it the wide. So it's just depends on the pending mechanism you have used. So another concept is multiple filter convolution. So it's also very easy concept. So we have an input vector. We want to use a convolutional layers to process this input vector. Definitely, we could use two sets of filters. The filters means the parameters. So it just means, okay, you can increase the filters number, you can introduce more parameters, then you could improve the capacity of your models. Oh, pooling is really the important concept, not limited to the CNN. Most of the time, in some other neural components, even in the LSTM, you also should use the pooling mechanism. So here we have, most of the time we have this pooling methods, such as the max pooling. You just given a vector, the max pooling says you should choose the maximum one of this vector, and you also have the min pooling, just take the average of this vector. And K-max pooling, you should just choose the top two maximum value. And dynamic pooling means, okay, you should partition the input vector into different groups and try to select maximum value from each of the groups. Okay, that's some concept in terms of the CNN. So for the transformer, here just highlight some important concepts for the transformer. The first thing is, actually, transformer is a composite module. It consists of, as you can see in the figure, the transformer consists of, the first is multi-head attention, and then is a normalization layer, and the third is a feed forward layer. So it's not a basic, something like the recurrent. It is a composite module, but in this module there is no CNN and there is no only the attention mechanism. So if you have recall that, as I have mentioned, that if your model has used attention, which just means you have incorporated the non-local bias to your model. And here, definitely, transformer, is reached in the non-local bias, but there is no CNN, no R, which just means, okay, the transformer lack of the local bias. So that's why if you want to use a transformer, most of the time the task should have provided a lot of training data, because it's lack of local bias, and local bias is important. So if you want to learn the local bias in a totally data-driven way, you should have more data. You should have more training data. Okay. So yeah, and the transformer also is a very important layers or component of the BERT. BERT actually is a multiple stacked component of the transformer layer. Just keep this in mind. Okay, transformer is rich in non-local bias, but like local bias. Most of the time, you should apply the transformer on some task which have maybe more training data. So in terms of the graph neural network, the GNN, okay, so the most important, the advantage that the graph neural network could bring us is, you could incorporate more relational bias or structure prior. So if your task is rich in the structure information, for example, the question answering, you could use a graph neural network. And another thing is, okay, transformer actually is a fully connected graph. You can something like this. In practice, a graph neural network is not very efficient to train, because it's not very easy to achieve batch training. You should use some specific or special code framework to do this. Okay, maybe another last question is, we have a lot of choices. How could we make different choices based on different scenarios? Here, some of my suggestions. So transformer is suggested when you have these scenarios. So if you focus on the machine translation task, definitely you should use a transformer, because most of the time they have a lot of training data. And then, if you have more training data, if you really want to design extremely deep neural networks, for example, in the language modeling task, you also could use a transformer, because this task they usually require a lot of parameters to do this. Oh, last point is, yes, best of both worlds, which means even you use a transformer, you also could use a LSTM. And in a lot of NLP tasks, we just make a combination between them. For example, in terms of the sequence labeling task, maybe the first layer is the LSTM, then followed by the transformer. So that is the best of both worlds. So when it comes to the LSTM is suggested when these scenarios. Maybe in most of the cases, you could use a LSTM, especially maybe you have the modestly sized data set. Last one is you could also combine the LSTM with transformer or with some other method. So in terms of graph neural networks, if your task really require a lot of relational bias, such as a question answering, you should know the relation between different name entities. This information really matters. So in this case, maybe graph neural network is useful for you, because you could incorporate this relational bias flexibly. Some other points similar to previous one. So in terms of CNN, right, it's a very interesting one. So because currently we usually use CNN as a word encoder instead of the sentence encoder. We use the CNN to capture some morphological information. We just use CNN to get the representation of this word. It's something like a character level or character aware convolution neural network to encode the word. So you can see a lot of scenarios which use a CNN to as a word encoder. Okay, last part is also some experience I want to share. So task-wisely, if you want to use a BERT, and if you focus on these two types of the task, you could first try to this framework, BERT plus NLP, and then try to this one. Just start with a relatively simple one, and then refine this framework later. So in this framework, there are two things you should keep in mind. One is usually we use the BERT should be fine-tuned and take care of your optimizer, because fine-tune, there are a lot of tricks when you fine-tune your model. So for tagging task, if you focus on tagging task, Flare always, performs better than BERT. So that's just one thing. So another thing is, if you focus on some tasks such as the abstractive summarization, instead of using the BERT, but maybe currently the SOTA word representation model, operation models is very useful. Usually you can achieve a better performance, but it's also require expensive cost to train this model. Yeah, if you don't have the BERT, just replace the BERT with the globe. And don't forget to use the UNBO. It is a very decent baseline. And if you use the tagging task, don't forget to use the CIF. I think that's all. And lastly, I try to set up two paper lists. One is for the word embedding. So this paper list, I will send the link to you later. So it's a collection of the papers related to the word representation. Another paper list is of the something like the cross-lingual, endangered language learning, or low resource language learning. So I just roughly collect of them, and maybe because I'm not sure later what types of tasks you will focus on. But if you want to know more, something or more background knowledge of your task you are interested in, the best way is just read more related papers. And here is a paper list, you could use it. Okay, I think that's all. Sorry, any questions so far?
Hello? Hello?
Hello. Yeah, I can hear you.
Yeah, I have a question. So when you're talking, in your slide, you're talking about GraphNet, and yes. So is GraphNet very good for things that relate to like discourse analysis?
For what? Discourse?
For discourse analysis. That you want to build domain around particular discussion in text.
Mm-hmm.
Is GraphNet good for something like that?
Oh, I'm not sure. The graph is very useful for, very useful when you really have a lot of relational knowledge. You want to incorporate this. You want to make full use of this. You want to tell your model that you should pay more attention to the relation between these two words. In this case, you should use the graph. There's no something magical in terms of the graph that, the graph just could help you make full use of your prior knowledge. So if you want to make a good full use of the graph network, you should first have a lot of prior knowledge, and you use it.
But you could argue that large documents essentially have some sort of structure, and like pronouns are used to refer to things in previous sentences and so forth. So you probably do need something like, if not something like a graph.
Yeah.
Especially because in coherent documents, you have like entities and concepts that get repeated over and over, and they all kind of like tie together, right?
Yeah, so it depends on your task, right? If your task is text classification, definitely I think you don't need it. But if you want to some fine-grained, the information extraction task, maybe it could be useful, right? Yeah, but just be careful. When you use the graph network, it really depends on the task setting, and maybe currently in natural language specific task, maybe some tasks such as a question answering or information extraction, these two tasks benefit a lot from the graph, or from the GNN. But maybe some others, I'm not sure it could work well for the motion translation because maybe it doesn't need to use it. Maybe, it should, I mean, carefully define what types of priority you want to incorporate. What the graph you have used. Maybe just use the syntactic graph. I don't think it would work well. Maybe you don't need it.
Okay, thanks.
So I think it's very interesting that you've categorized these neural network architectures as sentence representation. I've never thought of that before. And particularly when you mentioned that these are supervised methods. So just the whole local, non-local connection ways, and that's giving you context via which you can learn. So now I'm wondering, can you talk a little bit about the unsupervised methods? How do those work given,
As you know, I have listed two methods in terms of sentence level representation learning. The first thing is I think you can also use a BERT to collect the sentence level representation in an unsupervised way, right? So because if you use a BERT, you have a CLS token. So I mean, most of existing contextualized pre-trained model, you can obtain the sentence level representation from them. So that could be, I haven't listed here, but you can do this. So that's the first types of method. I mean, so you could get the unsupervised, you could get the sentence representation in an unsupervised way. Another is maybe these two models. The first is a paragraph vector. I think the author also has a paper what to vector is something like maybe a good representation of a document could also predict the representation of the words it contains, something like this. I mean, you just should pay more attention to what types of objective functions they have designed. So for the paragraph, that is, I mean, it's a good representation of a document that could also predict what types of a word it contains. That's the general idea of the paragraph vector. So for the skip sort, it's very, I'm not remember clearly, but something very simple, just something like predict what the next sentence is, or predict what types of word the current sentence contain. So because they are unsupervised method, right? So you cannot design some new things. You just predict the word in the sentence, or predict the word in the next sentence, or predict what the next sentence is, or predict something like this. You just predict.
So skip thought actually kind of like generalizes the idea of predicting the next word, like we have been doing in order to learn word representations at the sentence level. So it is trained so that you read one sentence and then you try to predict either the next sentence or the previous sentence. And this, of course, in order to be trained, requires that you actually have big documents, right? So that you don't just have like random sentences like often we have in machine translation that are not connected with each other. But if you have long documents, or even I guess a bunch of shorter documents in the language that you care about, then that's one really good way of connecting, learning sentence representations that learn to kind of like these connections across sentences that talk about the same thing, essentially.
So I mean, in terms of unsupervised method, there's no something, I mean, it's magic, just predict. Predict what the next word is, what the next sentence is, something like this. And also the same rule apply to the paragraph, I mean, for the sentence level word representation learning.
Yeah, that said, a little bit of supervision can really, really, really make the results much better. So, for example, because languages, paraphrases is a really good example.
Oh yeah, paraphrase. Yeah.
Yeah. So if you have, two sentences that essentially say the same thing, just with different words,
Yeah.
then even if you have a few thousand examples of these things, then you can train your model so that the representations that you get for each of those sentences are very close, right?
Yeah.
So even if you say it's raining a lot, and it's raining cats and dogs, or it's pouring, or if you say, like in Greek, it's raining chair legs. Yep.
Yeah.
Yeah.
I agree with you.
And you say, I want the representations for all of these sentences to actually be very close to each other, which would imply that their meaning is is the same. Then having that type of supervision can really, really improve your model. Of course, depending on what type of tasks you care about. But if we're talking about semantic tasks, these can be paraphrases, for example, and a little bit of supervision with them can be very, very useful.
Yeah.
Another task, which is still supervised, but it is used in like BERT and others, is entailment, or not in BERT, but it's entailment, right? So you can fine tune with a little bit and say, does this sentence imply that the second sentence is true, right? So if I say, let's say, I am flying home to Greece tomorrow, right? Or like, I came back from Greece yesterday. And this implies that in most cases, right, that I went through an airport, for example, right?
Yeah.
And having that type of information, and we can train a model with a little bit to say, oh yeah, these two sentences actually, one of them implies the other, or one of them negates the other. You can have something like, I don't know, Real Madrid won the Champions League, and then you can have Barcelona won the Champions League. But basically, this is like, I don't know, soccer, like football references. I hope everybody gets them. But basically, you cannot have two teams win, right? So these two sentences negate each other. If the first one is true, then the second one is false, and so forth. So having this type of like supervision, even for a little bit of sentences, can be very, very useful.
Yeah. I think emotion translation, this year you had a paper called Blue RT, right? I think it's maybe if you are interested in unsupervised sentence level pre-training, and you're also interested in the emotion translation, maybe you can read this paper. They have designed a bunch of maybe something like the weak supervision or weak reward when you want to train the sentence representation in an unsupervised way. Yeah, cool. It's something very interesting.
Do you all have more questions perhaps for Pengfei, or we could, if not, we can go on to do a little bit of exercises and play a bit with fast text.
Yeah, I think
okay,
Antonis,
so I have a question.
Okay.
With NBAO, I didn't quite understand its classification when it came to the whole topological versus connectional.
You mean this model? Yeah, if you use the NBAO, you just ignore many information such as the word order, the structure of the sentence. Yeah, you indeed you have ignored some important information. But for the text classification task, yeah, it could work well because maybe this information doesn't matter.
So basically, NBAO really just adds or averages all of the vectors in the sentence.
And it's considered supervised.
It's not supervised. Yeah, it could be supervised if you really care about the sentence representation, because you have already owned the word representation, right? And you just need combine them together. Average them. You have
but you didn't necessarily obtain the word representations in a supervised way.
Yeah, you mean the word representation? Yeah, you could use your globe or use a word vector. Then it's something like the supervised manners. You don't need additional learning parameters, but definitely finally you should have MLP layer. You should have a multi-layer perception. This need as additional additional signal to learn. But if we only claim that we only care the sentence representation. Yeah, you have already get a representation, and you don't need any other signals, just the average is word representation of the word wedge or globe. Right? You also can use some TF-IDF to weight this wedge word, but also don't need to learn them.